Hola. Bueno, creo que podemos empezar ya, ¿no? Y estamos aquí los detalles. Sí, ¿no? ¿Sí? Bueno, la charla de hoy la da Ken Voss, profesor emérito de la Universidad de Miami. Ken trabaja desde siempre en Ocean Color y entonces viene hoy aquí a presentarnos toda una presentación sobre la calibración vicaria de Ocean Color y en concreto sobre la boya MOBI, que es el único sitio de Vicarious Calibration que hay ahora en el mundo para satélites de color. Básicamente todas las estimaciones de clorofila que usamos vienen gracias a esto. Ken, como os he dicho, es profesor emérito en la Universidad de Miami, básicamente experto en óptica y medio ambiente. Es doctor por la Universidad de Texas A&M. Luego hizo postdoc en Scripps en el Voss Lab, que no sé los que decís color, es súper famoso. Y luego se movió a Miami. Desde allí, desde el 89 que está allí, ha sido PI del proyecto MOBI durante muchos años y siempre en general ha colaborado mucho en estos trabajos de Vicarious Calibration. Entonces toda esta ciencia que hay detrás de las medidas de satélite que hacen que estas medidas sean fiables, ¿no? Y nada, aquí está, ahora nos da esta charla de 1 horita y cualquier cosa. Pues. Gracias.
Thank you for the introduction, Marco, and for inviting me here. Can everybody hear me fine? Okay, thank you. So like I think he said, I will be talking about ocean color and the vicarious calibration and MOBI's role in ocean color. I'll try to give a little bit of why we have to do it, and then a history of the MOBI project, and then what the new instrumentation that we're doing and what we're doing in the future. So first, hopefully most know, ocean color, the opportunity ocean color is if you look at these water-leaving spectra, as you change the amount of chlorophyll in the water, the amount of blue light, as you increase chlorophyll, the blue light goes down because of absorption of chlorophyll, and so the water-leaving radiance is proportional to scattering over absorption. So in this region here, chlorophyll is up to about 0.1, you get a large decrease in the chlorophyll, so there's a great signal there that you should be able to tell the chlorophyll abundance in the water just by looking at the color. When the chlorophyll gets really high, you get extra scattering over here, so the red part goes up. But in general, this part is dominated by water absorption, and so this is the part that's sensitive. So it looks like a great signal there, and it should be easy to look at the water-leaving radiance and figure out what's going on. But if you look from a satellite, this is what you're seeing coming out of the water. This is what you're seeing at the top of the atmosphere. The atmosphere has added all of this stuff. And what should look like a really great signal at the surface ends up being sort of obscured by the atmosphere. And so we have to do atmospheric correction, and to get this part really accurate, you have to subtract this huge atmospheric signal. So it means the top of the atmosphere radiance must be measured really, really accurately. And so it's more accurate that you can measure than you can do by calibrating the sensor at the surface and just launching it. So we end up having to do this vicarious calibration process. As I said, you need very accurate measurements at the top of the atmosphere. You'd like to get the water-leaving radiance at the bottom to within 5%, and because of that other signal, that means you have to have the top to within 0.5%, which is more accurate than we can calibrate things. So what we end up doing is this post-launch vicarious calibration to be able to get the ocean color products that we'd like to get from satellite. So we have system vicarious calibration. It's basically a vicarious calibration of the entire processing. That's the important thing to know. we are going to take measurements at the surface. The satellite program is going to take their top of the atmosphere measurements. They're going to process it through their atmospheric correction routines and predict what the surface is. And then they adjust their calibration at the top of the atmosphere to match what we're seeing. But it's specific to whatever atmospheric correction routine you do. So whenever you change that, you have to do this calibration over again. Big thing for me is the input data has to be the highest quality to be able to do it. So, and you need a lot of measurements. This is an example from CWIFS, which was an ocean color satellite that NASA had. I think it was launched in '97. It's not working anymore. But basically, you can't just do this once. You have to do it a lot of times to be able to get the error down and the stability in this G factor, which is the top of the atmospheric gain. So it takes about 20 measurements till you've gotten this to be a reasonable sort of asymptotic, gotten to a good value. So you can't just do it once, you have to do it many, many times. To show what happens when you do this right, this is the VIIRS satellite, or VIIRS instrument on a NOAA 20 satellite, so a NOAA United States satellite. It's launched here. The crosses are the MOBI data from the site, which I'll show later. The diamonds, or the triangles and the circles, are the product from the ocean color processing from the satellite. The triangles are basically the operational product. The circles are the science product. You can see that things are pretty scattered here for each of the wavelengths. These are the channels on VIIRS. This is where they implemented some post-processing and some post-calibration from on-orbit stuff, and basically the science got a little bit better, the operational isn't very good. And then once we've done vicarious calibration on the satellite sensor, you can see that once we have enough data to do the vicarious calibration, you can see that everything is working out really well. So this is a process that has to happen basically on every ocean color satellite. So you need some source of really good data. You want the LW to be within 5%, so you have to have the data within that. And if you look at the different error contributions, it means the instrument, even if you have an instrument like this, depending on what's going on in your environmental situation, even a really good instrument is getting right to that limit. So you have to have extremely stable instruments and extremely accurate instruments. So with all of that, what happened? Why did MOBI come about? And basically, it came out of the first ocean color satellite, which is CZCS, that was launched back in the late 70s. In this, they didn't have an instrument like MOBI, and so they had to go to sea to try to collect the calibration data. And even with 60 days of ship time, they only ended up with 9 stations. So if you think that you have to have 20 to get a reasonable number, this is a fairly expensive way to do things. And you'd like to be able to track things, how well the instrument is working over time. So you really would like to have a continuous data set to work with. So Dennis Clark got the idea of that you really needed to have an autonomous platform. Dennis was at NOAA in the US. The requirements basically is you want to be able to collect and send the data back daily in some way. So for us, that means we have a cell phone link so we can talk to the instrument all the time and get the data back. You need someplace with clear sky because ocean color doesn't work without clear sky. You need homogeneous waters with a clean atmosphere. You need to have ships so you can get out to the buoy and have a reasonable chance of low sea state. And so basically the MOBI began when Dennis started development in 1985, which is a long time ago now. So if you think about an oceanographic instrument, how many instruments do you use now that are basically 40 years old? So this thing has been working. It started design there. NASA started funding it with one program, MODIS, in around 1990. So when he started development, he would just sort of scrounge money from whatever little pot of money he could find. This is when he really started getting money. CWIFS, another NASA program, gave us more money in '91. It was deployed off California, '93, first time in Hawaii, and then it's been in Hawaii since 1997, collecting data constantly. And it's been funded, initially it was funded by NASA, then it was funded by NOAA since 2007. And so for about 27 years, these two instruments have been giving us the primary data for ocean color Vicarious calibration. And they basically, there's two instruments, one goes in the water, one's on shore being worked on, and they keep switching back and forth. And it's been going, those instruments have been working fairly reliably for 27 years, and it was only in May of this year that we've actually switched to a new system. So it was quite successful. Where our site is off the island of Lanai. Here, it's within a good ship distance from Honolulu, where we can get ships from the University of Hawaii. Here's a picture of MOBI. It's a fairly large thing. It's about 15 meters long with these arms. I'll show another picture in a second. You can see it on the side of the ship there. We had have a site at the University of Hawaii Marine Center that allows us to do all the refurbishment and stuff there. So here's generally a cartoon of what MOBI looks like. Down at the bottom is an instrument bay that has the spectrometers in it. It has collectors at each of these three arms that measure both the upwelling radiance and the downwelling irradiance. And then it has another collector at the surface, which is measuring the downwelling surface irradiance. So by combining measurements from these arms of the upwelling radiance, we can predict or calculate what the radiance would be leaving the water up here. And then with the surface irradiance, you can get a measurement, combine the two things to get reflectance. At each of these collectors, light comes into a fiber, and the fiber carries the light down into the spectrometer down there. So there's only one spectrometer down there. The whole thing is in 1,200 meters of water. So here's the main mooring. Here's a tether that connects the optical system to the anchor, effectively. It has a cell phone link for our data. Now it's broadband. We can talk back and forth with the instrument to change parameters if we want. It's got an Argos to help us if the instrument break free. Occasionally the tether will be cut and we'll have to go and try to figure out where the MOBI is and recover it. Actually, in the last month, that happened 3 times because of the different hurricanes coming in and hitting it. So it's been a very busy month there. So basically, this is the instrumentation that's been out there. The optical system, I won't go over this very much, but the main point with it is there's 2 spectrometers. There's a side that covers the red side and a side that covers the blue side. And they have an overlap region. This one goes up to 640 nanometers. This one starts at 550. And with the overlap, you can sort of use both of the instruments to try to decide how good the data is doing. It's hyperspectral. It's about a 1 nanometer band pass, but with sampling every half a nanometer or so. And so with the hyperspectral, it's allowed us to do the Vicarious calibration for all the different ocean color instruments that have been launched. And we've been the primary source for both the United States and for other countries' instruments. The important thing with this instrument is that there's a mirror that changes position and changes, so that each of those measurements I showed you, the upwelling radiance at the 3 different arms, each of those has to be done sequentially. So we take a measurement of the downwelling irradiance at the surface, measure, say, the upwelling radiance at 1 meter, and then later make the measurement at 3 meters, or at 5 meters, and then at 9 meters. We can't do them all at once. So that was a limitation of this system. It's to get that data where it's been extensively characterized to make sure it's the best data possible. We look at stray light. We have NIST. We work very closely with NIST, which is the National Institute of Standards. In the U.S., it's our NMI, National Metrological Institute. So we work closely with them. We have divers go out every month and clean the collectors. This shows a diver working on the instrument. We have onboard sources that look to make sure its stability is stable, everything's good, and we've done a lot of characterization around the site. So we know this site really, really well. Here's close to 20 years of data. Each of the little dots is a measurement of the water leaving radiance over those 20 years. The black line there is basically 0 if you look at the average relative to this normalized to the average. The red dotted line there is a linear regression. It's over the 20 years, it's been very, very stable. This is -10 and this is +10%. So you can see it's barely moved at this location. So it ends up being extremely good for satellite calibration because we sort of know what we should expect, and if we see something off, there is variation around there. So as the satellite measures that site, you will see small changes. But in general, if something goes really wacky, we go and go look at the data closer to make sure it's not an instrument problem. There's the data we can post within 1 to 3 days, depends if it's a Friday or a Monday. We have to have somebody look at the data manually and do quality control, so it doesn't happen on the weekends all the time. And basically, it's all here, open to anybody who wants to look at it. And we generate a product that matches all the different satellites of anybody who asks us, and gives us their responses. So what's worked? We have the 3 arms, and so that we can look at the diffuse attenuation between the arms, and if everything's working really well, they all should match up really closely below 500 nanometers. They vary here because of a process called inelastic scattering. But if one arm is suspect, then you'll get this separation, and we can look to try to figure out which arm has a calibration error. But in general, we'll see situations like that. The 3 arms give us redundancy. This is the picture of the top arm and what it should look like. This is when we found that we lost our signal from the top arm, so we went out to look and discovered that the top arm had been missing. We're in an area off Lanai, which has fishermen, and the fishermen will go out there and I don't know if you have fish attraction devices here, we call them FADs. Whenever you put something in the water off Hawaii, and probably off here too, it becomes a site where you get small fish accumulating, and once you get small fish, you get larger fish, which attracts fishermen. And so we'll have situations like this occasionally that a fisherman will get too close to the buoy, even though we have big signs saying don't go there. So some fishermen must have hit the instrument and broken it off. But we still have the middle and the bottom arm, so we can still produce data. Oops. So we've had this, basically pretty close to the same team has been working on the data since '97. And so we have a very stable group of people that have a lot of experience now. The weather's is good in Hawaii, so we can get to the site and work on it pretty reliably. We have this close collaboration with NIST, which has been very useful. We have internal sources to try to maintain stability, and the ratio of when we calibrate the instrument for a deployment and then after has been very stable, within, on average, about a 0.7%. And as I said, there's an overlap region between the two spectrometers, which lets us check how each spectrometer is working to a certain extent. And it also taught us about stray light. Another thing that's sort of interesting is the site's far enough away from casual recreational boating, but unfortunately, or whatever, there still are some people. We went out one time to do a check on the buoy, and we found that the tether, which is a polypropylene line about that big around, we found this knot in the middle of it and didn't know what was. Obviously somebody came and tied a bowline, two bowlines to tie it together, but we weren't sure what the scoop was. One of our team members went to the big island of Hawaii, and went to a couple bars where the fishermen hung out and started talking to the fishermen to find out what had happened, to see if they could learn anything. And apparently what happened was a fisherman had gone out, gotten his propeller caught in the tether, okay? And so to get it free, he cut the tether and just let it float away. Another fisherman who went out there a lot was nice enough to grab the tether, tow it to where it was supposed to be, and tied these knots for us. So we never even knew anything had happened. But it was a great that we didn't have to spend the money to go and retrieve it. But we do get fishermen and things that hit the arm. This is a cracked collector from here. But in general, we hope that most of the people who are out there have an idea. Occasionally, we've gone out to do, every 6 months, we have to swap a buoy in and out. And we've gone out there and been diving on the buoy and had other fishermen come by and yell at us, telling us we shouldn't be around there, we shouldn't be working on this, and to leave it alone because it's an important resource. And like, no, we're supposed to be here. This is good. Okay. So that's been the Moby history. What we're doing now is our improvements. NOAA is supporting the Moby refresh, basically a whole new optical system and buoy structure for Hawaii. We deployed the first one of these in May, so it's the first time a different instrument has been at that site since '97. NASA's supporting Maronet, which is basically the same new optical system and buoy structure, but we're going to put it off of Perth, Australia. And the idea is that if you look at, in Hawaii, in the northern hemisphere, parts of the year, the glint from the surface is so strong because the sun is basically right overhead, that site in the summer is not very good. But if we put one in Australia, in the southern hemisphere, then that time of year when this one's not working, this one will work well. And it gives redundancy. So that instrument, I have almost our whole team, other than me, are in Australia right now. And the instrument should be deployed, I think currently it's scheduled to be Tuesday because of weather problems we've been having. But we're supposed to deploy it in there. We're building 3 or 4 of these instruments for the Hawaii site. NASA, we're building 2 of them. And with NASA, we had to make sure we got down to 350 nanometers for PACE. NASA is supporting it under their PACE project, PACE satellite mission. And we needed to be able to fit in a container so that we could move it down there. And we also have it such that the optical system can be removed intact, but we're not really going to use that feature. So the new spectrometers use this thing called a inline volume holograph. So basically, you think of 2 pieces of glass and then the gelatin between the 2 pieces, and you imprint an index refraction gradient along there. So that's your diffraction grading. And they end up being extremely good imaging quality through there. So you think of light coming in and it'll diffract depending on the wavelength. So here's a false color picture of one of the spectrographs, and each of the collectors now can be acquired at the same time. So you can take one image and get all of the 7 different measurements. We don't have that sequential issue. The measurements end up having much less noise. And so that's the advantage of this system. It's also supposed to be extremely stable. Here's some pictures for a while. Here's the spectrometer. It doesn't really do too much for you. There's fibers coming in here. They go to the grating and through that to the camera back here. Here's a blow up of the camera. Here's the spectrometer with the grating in it. Camera, CCD camera, we use the same cameras used for astronomy, and we cool them to minus 60 degrees C. So it has cooling fins that dump the heat to the water, outside water. There's a single board computer in here. This is the same picture, but now with copper tubes to bring the heat back to those cooling fins. Here's a picture of one of the spectrometers being built up. Back here is that camera, and the cooling fins would be off here eventually. In the front is a bunch of electronics and then a shutter plate that allows us to choose which of the channels we are going to be measuring at that time. Same thing effectively, but now you see the titanium housings being installed on it. And so we have one of these for the red and one of these for the blue spectrometer on the instrument. There's these little splitters that take the input fiber light and split them between the red and the blue spectrometer. The splitter basically has a polka dot mirror in there. So you take the light and you shine it through this polka dot mirror, and the polka dot mirror will take some of the light and reflect it back down, and some of the light and let it go through. And it looks just like, well, I don't know, anybody, you know what a polka dot is? Okay, so it's a mirror that has little silver dots all over it. So the dot will reflect part of the light, and then the place where there isn't a dot lets the light go through. Anyway, so there's those. This shows one installed on the back of the splitter housing. This is the external part of the housing. The fibers from the different arms comes here, will be attached up to here, and then the 2 spectrometers are attached here and here. And inside the splitter housing, we have all the different light sources to make sure, and LEDs, an incandescent lamp, and there's also a mercury lamp to allow us to measure the stability of the instrument while it's at sea. Here's a picture of the instrument built up. There's the splitter housing, the 2 spectrometers. There was no reason to make this light, and so basically this weighs about 300 kilograms or so. It's not a a portable instrument at all. And so there's that. Part of the characterization is spectral stray light, which means basically we take a laser like this that you can computer control and tell what wavelength to put out. We go from 250 to 900 nanometers, sending in a single line from the laser, and then seeing what shows up on the spectrometer, so you can characterize that and correct for it. You end up with a matrix like this, which is a nice, you invert to correct for stray light. We also have a nice little hot tub for the instrument to do thermal characterization. And this shows a prototype with PVC housing, anyway, being dropped into it to be characterized. The instrument's stable. The wavelength, the new instrument has 1 nanometer, still about 1 nanometer bandwidth, but has samples every 0.3 of a nanometer. And we look at a Fraunhofer line, solar Fraunhofer line, to measure stability. And basically, this is 149.3 pixels versus 148, and you can see that it did vary slightly over 4 months, but it was relatively stable within a half a pixel, which is on the order of 1/10 of a nanometer. So the instrument is extremely stable. It's working out really well. We did a crossover between the new instrument and the heritage instrument, and basically the water leaving radiance here is probably, you can see that the new instrument is the R's and the M's are the old instrument, and they basically lie right on top of each other. So basically we validated that the new instrument works the same as our old instrument, so that in terms of overall quality, so we can maintain our data record that we've got. So the directions the project's going, as I said, we've installed one of the new systems in Hawaii in May, so now that's working with the new instrumentation. We are going to be installing the new one next Tuesday. UMedSat is actually working to get a very similar system, and we're working with them in their procurement process. We can't supply it. It has to be supplied by a European country or company, so we're just helping them see what our specs are and how we built it, and it'll be either off of the Canary Islands or off of Crete, probably by 2029, the way that project seems to be going. So with 3 sites, we'll have more rapid initializations of satellites and some redundancy. But as opposed to a lot of buoys, this one's fairly expensive. The projects are on the order of $2 million a year or more to maintain. So, conclusions. Basically, MOBI's provided the Vicarious calibration for all the ocean color sensors, all the international ocean color sensors, since 1997. We have this great time series that we can look for trending, although there seems to be almost no trending at that site in Hawaii, which is good for Vicarious calibration, not real interesting from other points. We have this dedicated group of people that have been working with this system for a long time, so they know what's going on. We're right now running into the problem, though everybody's retiring, so we're having to replace people. And just as importantly, we've had nice continuous support from NASA and NOAA over these many years, and a lot of dedicated people inside those agencies. You know, I don't know if you have time series. It's really hard to keep a time series going because in a way they're not, especially a site like this, it's not real interesting other than this utility as a Vicarious calibration site. So it's really important that we have people that understand that you need something like this and can help us keep funding. So that's basically it. Thank you for listening. I hope I didn't talk too fast. I'm sorry I can't speak Spanish. I lived in Miami 30 years. You'd think I'd learn Spanish. All my neighbors spoke Spanish, but I never managed to have the time, it seemed. So, thank you. Any questions? It's not really a question type talk.
I will ask out of ignorance, basically. So how can you use the different sites? You say that you would have some way of replicating or duplicating data. So, but this is basically to get the vicarious calibration from the upper atmosphere thing, right?
Mm-hmm.
So is it exactly the same at the different places, or how does it work?
So part of the ocean color processing system takes into account the illumination geometry and the what we call a bidirectional reflectance, the variation in the light coming up from different angles. So even at Moby, every time at the one site, every measurement is sort of adjusted for the illumination conditions. So that's one thing that has to be done between the different sites.
But you're not looking at the same place in the atmosphere.
No. You try to choose times when the atmosphere is both a low aerosol content. So you try to choose times when the aerosol optical depth is less than 0.1 at 500 nanometers. And where you have a maritime atmosphere where the atmospheric correction should work for you. But you're right, it does depend on the atmospheric correction working in each of these different sites. Currently, what we have is a situation where we have the one site and then other validation sites, such as the C-Prism sites that you might be familiar with, because Marco has one. And those are used for validation for checking the atmospheric correction in different locations. But with the three sites Hawaii for sure, and then Perth, and the Canaries, and you'll have to, for the Canaries and for Crete, you'll have to pick times when there isn't a big Saharan dust outbreak and try to find the times when it's just a nice maritime atmosphere. The European sites could get very, very complicated very quickly. There's going to be three sites, so hopefully they all work, and it'll be interesting to see how we use all three sites when they get up.
The Perth side, do you get dust in the atmosphere?
It's supposed to be pretty clear. We have a Aeronet station. The Aeronet, what's that? No, it's going to be, the Aeronet site's going to be at Rottnest Island there, which is just very close to where our measurements are going to be. And we'll be able to be looking at the atmosphere correlated with that. Everybody always tries to say we need the atmospheric measurements along with our vicarious calibration measurements. We used to have one in Hawaii, and nobody ever used the data, but NASA's requiring us to have one there. So we'll find out more, but from historical looking back at data, it should be a pretty good site. We're hoping it's a good site. NASA's hoping it's a good site. We need someplace where we have somebody who has expertise close. And David Antoine is now at Curtin University, and he has a lot of experience through the Bosol site and such. So we'll see. This was the goal. Anything else?
Well, I have one question, a simple question, just, I mean, we are about to build a network of operational oceanography at regional level, so it's something that we hope will last 40 years as the movie side. So, well, my question is simple, is what's the main difficulty, I mean, to guarantee this 40 years of operation? I mean, technical, the
Number
personnel?
one?
Yes, money.
Number one is funding. Trying to keep funding going for that long for a site like that. You look at in the U.S., maybe it's easier here, I don't know. You look at the U.S., there's 2 sites that for ocean color we've had, that have had biological and some ocean color, which were the hot site off Hawaii, the Hawaii Ocean Time Series, and then there was the BATS site, the Bermuda Atlantic Time Series. The BATS site's no longer operational because funding died off after so many years. The hot site is still active, but it's a struggle to keep funding going for a time series. Agencies want something new and fancy, but maybe the Europeans can do it better, I hope.
Well, the idea now is to have 20 years at least.
20 years? That'd be
Yes,
great.
operation.
20, still, it seems to me from the outside as you have longer funding cycles than we have. Our funding cycles are between 2 and maybe you're lucky 4 years. If 4 years for NASA projects, 2 years more NSF and such, so you're continually having to redo it. It seems, when I look from the outside, it seems Europeans do it longer, but I hope so. That's a hard thing. And keeping people, too, involved. And having, that's hard. It helps with stable funding, but keeping the same people involved. Do you have the restrictions? Maybe I should talk to you off the line with this, but do you have the same restrictions? I know with the Busol project, there was actually a limitation for how long you could have somebody work on the project. Like every 3 years, you had to have rotating engineers and such?
No, we don't think so, no.
Okay, that's good, because that would make it really, really hard. So, anything else? Thank you for your attention. I mean, this is not anywhere near probably where any of you work, so I appreciate you coming out.
Bueno, gracias.
Okay?